How can we find the zeros of a polynomial function written in standard form? That's our big question. Now here we have f of x, which is written in factored form, and g of x, which is written in standard form. If we click on f of x, here's the graph. And then if we graph g of x, we don't see the graph of g of x. Now let's hide f of x, and we notice that g of x is hiding underneath it. So that means that f of x and g of x are the same exact graph. And therefore, f of x and g of x are equivalent polynomial functions. Only they are written in different forms. So f of x is written in factored form and g of x is in standard form. Now, we notice that in factored form, we can quickly identify the zeros of the function. So if the linear factor is x minus 3, we know that 3 is a zero of the function, and the graph will validate that for us. So here's a zero of the function. We know that this is a zero because the y value is 0. So for the linear factor x plus 5, we know that negative 5 is a zero of the function, and our graph validates that negative 5 is a zero of the function. And last linear factor is x minus 2. So we know that if x minus 2 is a linear factor, then 2 is a zero. And again, the graph validates that for us. Okay, so again, in the factored form, we can quickly identify the zeros of the function. But if we look at the standard form, what does it reveal to us? Now, how many zeros did we have here? We know that we have 3 zeros. And in the standard form, the highest exponent is 3. This is the degree of g of x, or the degree of the polynomial function. So we have observed in the past in all of the polynomials we have worked with that the degree is the same as the number of zeros. So this is validated again by this graph, that if the degree is 3, there are 3 zeros for the function. And that's all that we can see right now. All right, let's take a look at some other examples. So again, here f of x is in standard form, is in factored form, and g of x is in standard form. If we graph f of x, this is what we see. If we graph g of x, okay, where is it? It is hiding underneath f of x. So that therefore, f of x and g of x are again equivalent functions. Now, if we look at the factors, x minus 3 gives us the 0, 3, which is right here. The factor x plus 5 gives us the 0, negative 5, which is right here. And the factor x minus 2 will give us the 0, 2. And the factor x plus 2 will give us the 0, negative 2. So there's 1, 2, 3, 4 factors, or rather 4 zeros. Okay, if we look at g of x, we don't see those numbers. The zeros are not very obvious, but the degree of the polynomial is 4, and we notice that there are 4 zeros. Okay, so 1, 2, 3, 4. So far, what the standard form revealed to us is the number of zeros. Now let's take a look at another example. Here we have f of x again in factored form and g of x in standard form. There are, for f of x, there are 1, 2, 3, 4 linear factors. So how many zeros are we going to find? We're going to find 4 zeros. So let's see first if these are the same function. So here's the graph of f of x. And then here's the graph of g of x, which we don't see again. But if we hide f of x, g of x is hiding underneath it. So again, the picture validates to us that f of x and g of x are equivalent functions. For f of x, we notice that x minus 1 is a linear factor, therefore 1 is a 0 of the function. So here's that 1. If x plus 2 is a factor, then negative 2 is a 0 of the function, which is right here. And then x minus 3 will give us the 0, 3. And x plus 1 will give us the 0, negative 1. All right, so here are the 4 zeros of f of x. Now, we don't see any clue as to what the zeros are if we look at g of x. However, the degree 4 tells us how many zeros there should be. Okay, let's move on to the next one. Okay, here we have f of x again in factored form and g of x in standard form. So this is the graph of f of x. And the graph of g of x is hiding again. Let's find out where it is. And it's underneath f of x. So therefore, f of x and g of x are exactly the same graph. And therefore, they're exactly the same function, only written in different forms. Now, in this factored form, we notice that, it's not quite easy to identify the zeros. The only one that's easy is this one, x minus 2. If x minus 2 is a factor, then we know that 2 is a 0 of the function. So how do we know what are the zeros for these two factors? For those two factors, we'll say that 2x minus 1 is equal to 0 because we're looking for the 0 of the function. So we need to add 1 to both sides to solve for x. So we'll have here 2x equals 1. Therefore, we can divide both sides by 2. And so x is equal to 1/2. So one of the zeros is 1/2. And if we click on that, where is 1/2? 1/2 is right here, which is 0.50. Okay. Now, the next factor is 3x plus 4. So to find the 0 of f of x, using the factor 3x plus 4, we say 3x plus 4 is equal to 0. Therefore, we subtract 4. 3x equals negative 4. We divide both sides by 3 and we get x equals negative 4/3, which is 1 and 1/3, negative 1 and 1/3, which will give us about negative 1.33, so on and so forth. Okay, so let's click on the last x-intercept of f of x, and it's right here, and negative 1.333. So again, f of x revealed to us quickly what the zeros of the functions are. Only some of the factors we have to solve for x, but that's okay. Now, if we go to the standard form, it doesn't reveal to us the zeros, but it gives us the degree, which is representing the number of zeros. And so here we have 3, and the number of zeros is 1, 2, 3. All right, so let's go to the next slide. Okay, in this slide, we don't have, okay, let's erase this. Okay, so in this slide, we don't have the function written in standard form, or rather in factored form, only in standard form. So this is the challenge for us. What we're going to do is find out how we can convert this to factored form by finding first the zeros of the function. The only thing that we know so far is that the degree of this polynomial is 5, and therefore we should find 5 zeros. So that's our claim right now, that if the degree is 5, we should be able to find 5 zeros. All right, so now we move on to this worksheet that I gave you. We fill this up based on those functions in the activity builder. So here's our first function, but we only want the standard form. These are the zeros. Number of zeros is 3. Degree of the polynomial is 3. Okay. All right. So we're going to look closely on the standard forms so that maybe find a way as to how we can find these zeros. How can this lead us to the zeros that we have here? Okay. Let's review another thing that we have observed before. We said that the number of zeros, the number of positive zeros is the same as the number of sign changes in the standard form. So let's just quickly check that. In g of x, the first term is positive, the second term is negative, and this last term is positive. So how many sign changes is this? From positive to negative, that is one change. And then from negative to positive, that is another change. Therefore, in this g of x, there are two sign changes. Therefore, we should expect 2 positive zeros for this function. And if we check our zeros, we see that 3 and 2 are positive. Indeed, we have 2 positive zeros. Okay, let's see if that works for the rest of the functions. So let's find the signs. So positive for the first term, positive for the second, negative for the third, negative for the fourth, and positive again. So now we look at whether the signs are changing. So positive to positive, no change. Positive to negative, that is our first change. Negative to negative did not change. And negative to positive, another change. So there are 2 sign changes. Now let's take a look. How many positive zeros are there? There are 2 positive zeros. All right, so it worked for our claim that the number of sign changes is the same as the number of positive zeros worked for this first 2 function. Let's try if it works in this next 2 functions. So first term is negative, second term is positive, positive, negative, negative, negative to positive, change. There's a change, so first change, positive to positive, no change, positive to negative, another change, and negative to negative, no change. So again, there are 2 sign changes, and if we look at the number of positive zeros, there are 2 of them. So again, it's validated here. Is that claim going to be validated on the fourth one? So let's check. Okay, first term is positive, second term is negative, then positive. Okay, for positive to negative, that's our first change. Negative to negative, no, it didn't change. Negative to positive, it changed again. So now there are two sign changes. And if we look at our zeros, there are two positive zeros. So we are claiming that the number of positive zeros is the same as the number of sign changes. Now, for the last one, okay, we don't know the zeros, but we can tell what the degree is. The degree is 5. Therefore, there should be 5 zeros. And then if we look at the sign changes, this is positive, negative, negative, positive, negative, negative. So there should be one change. This is our first change. No change here. And then here, changed again, and changed again, and then did not change. So there are 3 sign changes. Therefore, 3 zeros should be positive. So there should be 3 positive zeros, and therefore there should be 2 negative zeros, since there are 5 zeros altogether. All right, so let's fill up the last column. Okay, in the last column, you are asked to find the factors of the constant term and the factors of the leading coefficient. So here is the constant term. Okay, 30 is the constant term, and the leading coefficient is 1. Let's just call this leading coefficient. This is the constant. So we want to list the factors of 30. So what are the factors of 30? I have some space. Okay, let's just do it here for now. So factors of 30. So what numbers go into 30? 30 is divisible by 1. 1 times 30. Okay. 2 times 15. 3 times 10. 5 times 6. These are all the factors of 30. So 1, 2, 3, 4, 5, 6, 10, 15, 30. Now, how about the factors of 1? The leading coefficient is 1. So that's only going to be 1. Now, after finding the factors of the constant term and the leading coefficient, we are going to divide them. When we divide, we are getting the ratio of the two. So 1 divided by 1 gives you 1. 2 divided by 1 is 2. 3 divided by 1 is 3, so on and so forth. So therefore, the ratios are 1. Okay, let me just write it here. 1, 2, 3, 5, 6, 10, 30. These are the positive ratios, but we are going to include in our list the negative ratios as well. So instead of putting positive and negative to every single one of them, we're just going to enclose this in braces. And then we're going to put positive, negative. That means we are listing all the positives and all the negative numbers here. Okay, so these are the ratios of the factors of the constant term over the factors of leading coefficient. Now, Let's look at the zeros. So let's go back to the zeros and find out if these zeros belong to the list. So do we see 3 in the list? Yes, 3 is right here. Do we see -5 in the list? Yes, we see 5 in here. And we include the negative, so this also counts as -5. And 2 is also in the list. Did we find a zero that does not belong to the list? No, all the zeros are in the list. So is this observation going to hold true for all of them? Okay, let's find out. In this one, our constant term is 60, and the leading coefficient is 1. So if we want to find the factors of 60, so what are the factors of 60? Factors of 60 are 1. So it'll be the same as the factors of 30, only we need to include 4 because 4 divides 60. 60 divided by 4 gives us 15. And then also 12 and 15. And then when we divide it by 1, we're just going to have exactly what we have for the factors of 60. So to generate that list, we're going to have positive and negative. Okay. 1 over 1 is 1. 2 over 1. 3. We include 4. 5. 6. 10. 12. 15. 30. And 60. And I forgot 20. 20 also goes into 60. So let's put that down, 20. Okay. So now here's our list of the ratios of the factors of the constant term over the factors of leading coefficient. And now we look at our zeros. Is -5 in the list? Yes, it is in the list. Is -2 in the list? And we see -2 right here. Is 2 in the list? Yes. And 3 is also in the list. So all of these zeros are in our list. Okay, so let's go to the next one. Here the constant term is 18. And the leading coefficient is -3. Okay, but when we try to find this, we just want the factors of 18. So maybe, I don't know, what are the factors of 18? So let's do it here. 18 would be 1, 2, 3, 9. I forgot 6. 6, 9, 18. And then we want the factors of 3. Because the leading coefficient is 3. The factors of 3 are 1 and 3. Okay, and then we want to divide the 2. Divide the factors of 18 by the factors of 3. So 1 divided by 1 gives us 1. 2 divided by 1 is 2. 3 divided by 1 is 3. 6 divided by 1 is 6. And we'll have 9 here and 18. So now we're done dividing by 1. But there's another factor here, which is 3. We need to divide every single one of the factors of 18 by 3. So 1 divided by 3 gives us 1/3. And 2 divided by 3 gives us 2/3. Now 3 divided by 3 is 1, and we already have it. 6 divided by 3 is 2, and it's already in our list. 9 divided by 3 is 3, which is already in the list. And 18 divided by 3 is 6, which is already in the list. So this is our list of the ratio of the factors of the leading coefficient of the constant term and the leading coefficient. So if we list them here, we're gonna have here plus or minus. Okay, 1, 2, 3, 6, 9, 18, 1/3, and 2/3. Now let's take a look if all our zeros are in the list. So is -2 in the list? Yes. Is -1 in the list? And yes, we find -1 here. 1 is also in the list, and 3 is in the list. All right, notice that here we only have whole numbers or integers, and here also all integers. But here we have integers and some fractions. We call the fractions rationals or rational numbers. Okay, so let's go to the fourth equation here, or fourth function. Let's just erase this. So here the constant term is 8, and the leading coefficient is 6. So the constant term, for the constant term 8, the factors are 1 times 8, 2 times 4, so 1, 2, 4, 8. And for the leading coefficient 6, the factors are 1, 2, 3, 6. Okay. Now we are going to divide them. And so what we're going to get is, okay, 1 over 1 is 1, 2 over 1 is 2, 4 over 1 is 4, and 8 over 1 is 8. So we're done dividing by 1. We don't do divide by 2. 1 divided by 2 is 1/2. 2 divided by 2 is 1, which we already have. 4 divided by 2 is 2. We already have it. And 8 divided by 2 is 4, and it's already in the list. So now we're done with 2. We now divide by 3. So 1 divided by 3 is 1/3. 2 divided by 3 is 2/3. 4 divided by 3 is 4/3. And 8 divided by 3 is 8/3. So now we're done with 3. We now move on to 6. 1 divided by 6 is 1/6. And 2 divided by 6 is 1/3. We already have that. 4 divided by 6 is 2/3. And 8 divided by 6 is 4/3. So this is our whole list. So we put them here. So we'll have 1, 2, 4, 8, 1/2, 1/3, 2/3, 4/3, 8/3, and 1/6. Now are these zeros in the list? So let's see if 1/2 is in the list. Yes, 1/2 is in the list. -4/3 is in the list, and 2 is also in the list. So all of the zeros are in our list. So How does that help us determine the zeros for this? We don't know what the zeros are. So far, we only know that there should be 5, and there should be 3 positive zeros and 2 negative zeros. Okay, so that means that we could just generate the list and then test if if any of them will give us a zero of the function.